Hey everyone, this is Christian bringing you another webinar on catalysis. So today we'll talk about the general subject of catalysis, and since my favorite area is heterogeneous catalysis, the presentation will lean towards that, but I'm sure you will also get some input on general aspects of catalysis as well as homogeneous catalysis. But before we get started, let me just say that in your control panel under handouts, you can download the slides that I'll be showing you and also an introduction compendium, some 30-40 pages on catalysis that you can feel free to share with whomever you want. But with that said, let's get started. So I represent a company called Hulteberg Chemistry Engineering, and we specialize on heterogeneous catalysis. We work all the way from research through production, upscaling, whatever you want, and we can help you anywhere from idea to implementation. With that said, let's get started with today's outline. So we have first an introduction, giving you some background to the subject. We will be going through some general considerations. Then we will touch upon homogeneous catalysis and the reactions involved there. And finally, we'll talk about heterogeneous catalysis, like the structure, what components make up a heterogeneous catalyst. We'll talk about development and testing, manufacture, and also a little on deactivation. And each of these will be more developed in future webinars in the upcoming weeks. So to start, catalysis is really involved in a lot of different processes. The largest catalytic process is the photosynthesis, but it's also omnipresent in any processing of fuels and chemicals. So transforming raw materials into consumer goods as well as bulk chemicals. We use catalysts. And that's very obvious on this next slide here. So if we look at the chemical industry, we have a few raw materials. So petroleum, natural gas, oxygen, nitrogen, and sulfur. We make a few commodities of these, benzene, toluene, xylene. We produce ethane, ethylene, and the like. To secondary commodity chemicals, they all branch out into a lot of different intermediates. And finally, we end up with smaller volumes of different consumer goods, where we combine all of these different chemicals into products. So from left to right, we have huge volumes, rather low prices per ton. And the further right we get into this picture, the lower the volume, the more complex the molecules, and the higher the cost of the chemical. And if you look at all of these little orange dots here, that's where we have catalysts involved in the transformation. So it's no lie to say that there is definitely a lot of catalysts involved in transforming chemicals or raw materials into chemicals, especially for bulk chemicals. If we look at the subject of catalysis, it has been developed over about, well, almost 200 years now. The first reports were made in the early 19th century, and one of the first definitions given was Swede, Jens Jakob Berzelius. He said that a catalyst has the ability to awaken affinities which are asleep at a particular temperature by their mere presence and not by their own affinity. So to put it in other words, a catalyst is something when it's present in a small amount causes a large change, and it's not consumed in the reaction. It only helps the reaction to get going. The initial definition, though, does not cover what we see in the industrial case. In the industrial case, we have slow deactivation. So in practice, there is some change to the catalyst, but it's much slower than stoichiometric. So industrially, we change the definition so that a catalyst is a substance that increases the rate of reaction towards equilibrium without being appreciably consumed in the process. So appreciably being the key word here, that it takes much longer than if it was involved stoichiometrically. And to be quite honest, as catalyst suppliers, we kind of appreciate this deactivation because it means that we're allowed to sell more catalysts. Lifetimes are ranging from half a year to 5, 6, 7 years, depending on the process and the operating conditions. Another important consideration or concept is the active site. The site forms a complex with a reactant and a product is formed. So you have a site where the reactant is mostly chemisorb, but it can, on some rare occasions, also be physisorb. But the site of the catalyst interacts with the reactant. It forms some kind of complex or new structure, and then the products are formed through chemical reaction. Could be interaction between two different reactants, and the site is restored. And that's really a key sentence. The original site is restored. So by reforming this site again, we can actually reuse the catalyst many times. Catalysts can come in all sorts of shapes and forms. It can be like protons. We can have Lewis or Brønsted acids, both solid and liquid acids. It can be organometallic complexes. It can be organic or inorganic polymers. Enzymes are very common catalysts in our bodies and in all biological systems. It can also be inorganic materials. And if you look at it, they can be different in complexity. So we have enzymes, which are basically folded proteins that do very shape selective catalysts. We find some organic catalysts. We find rhodium complexes. We also find homogeneous acid catalysts, and these are all homogeneous materials, so they exist in the same phase as the reactants and the products. Then we have structured catalysts, solid acid catalysts, which has well-defined crystalline structures called zeolites. And we also have the supported catalysts, where you have an oxide on the bottom, in this case alumina, and on top we place some kind of metal, in this case platinum, and it's the metal surface area that gives us the catalytic effect. So the changes to the catalyst are far from stoichiometrics, so that's sort of one important factor that we need to consider in catalysis, and otherwise we are not in catalytic operation. But we also need to exclude things like hydrogen peroxide, ozone, that is used to initiate polymerization reactors or reactions, because they are not reformed after the reaction. So an initiator, even though one molecule of initiator creates a large effect, it's not a catalytic effect because it's not reformed after the reaction. In the strict sense of catalysis, we also exclude heat, microwaves, and photochemical. But in the definition, or what is called catalysis, then there's a special section of catalysis called photocatalysis, where you combine these two subjects. Catalysis does not do magic, so we can't do anything to change nature, which is basically the ultimate equilibrium of the reactions. The catalysts, they only accelerate the rate of approach to equilibrium. So we help navigate the energy landscape in a better way, saving energy, lowering activation energy of the reactions. But we can't change what we do with nature. We can, however, find catalysts that are selective to one part of the possible space and very little selective to other parts. We differentiate between homogeneous catalysis and heterogeneous catalysis. In homogeneous catalysis, the catalyst and the reactants and the products are present in the same phase. So you have most commonly a liquid phase where you add a catalyst like an acid or a base or some kind of organometallic complex, and they're all swimming around there together doing reaction over a considerable period of time. The good thing with homogeneous catalysts is that you have very good contact between the catalyst and the reactants and products. The drawback is, of course, that it's difficult to separate the catalyst from the reactants and products afterwards. In heterogeneous catalysis, the catalyst and the reactants are in different states of aggregation. Usually it's solids acting on liquids or solids acting on gaseous reactants and products. And catalysts can be anything from oxides to metals to supported metals. But let's go back to this statement that we underlined earlier, that the original site has to be restored. It's true that it has to be restored, but this should not be interpreted like that there's no change at all to the site. So actually there's quite a lot of change. So metals, they may recrystallize, oxides may lose oxygen, and in homogeneous catalysts, they undergo a large number of reactions. So even though the original site has to be restored, it doesn't mean that there is no change. The key thing is that it has to be a cycle. So the catalyst has to be restored after undergoing the catalytic cycle. Other important aspects are activity. So activity is the rate with which the catalyst causes a reaction to proceed towards chemical equilibrium. It's usually kilogram per second and cubic meter or mole per hour or liter. And this activity is strongly dependent on temperature, pressure, inlet concentrations, etc. And we can define this in many different ways. Either we define it at a standard condition, so at a certain temperature, pressure, and catalyst volume, or we may report it as a single rate constant, which is sort of the true kinetics, but that is a very difficult thing to measure in real life, in practice. So we'll come back to how you can do that in our catalyst testing webinar later on. You can also express the temperature for achieving a certain conversion. For instance, at 300 degrees, we reach 50% conversion for this catalyst, but for catalyst B, we only need 270 degrees to go to 50% conversion, meaning that catalyst B is more active than the other catalyst. And we can also finally give the amount of catalyst for converting a given inlet feed at a given operating temperature and pressure. So we have two different catalysts. One requires 15 grams of catalyst to convert the feed at the temperature and composition that we decided, but another catalyst only needs 5 grams. So the lower weight is, of course, the more active catalyst. But activity is not important. Well, it's important, but it's not the only measure. So activity without selectivity is pointless. So selectivity is how much of the desired product is actually formed. So selectivity is defined as the number of moles of A, which is our reactant, that is converted into B. and divided by how many moles of A is consumed. So for instance, ethanol can be reacted either to acetaldehyde or ethylene, and then we have, for instance, a desire to produce acetaldehyde over ethylene. Then we need to know how many of the ethanol molecules consumed actually forms acetaldehyde. And selectivity is actually determined based on the resulting products, but we have another measure, which is yield, which is perhaps more industrially relevant because it actually has the same numerator, so the number of moles of B formed on the above the line, and then of course instead of having the number of moles of reactant converted, we actually take all of the number of reactants coming into the reactor instead, because unconverted material is also problematic, and it's also to some extent considered a loss, even though you can recover it by separating it from the products. So yield is a more industrially relevant measure. We also talk about the turnover number. It's the number of times a homogeneous catalyst can convert reactant A to product B. In heterogeneous catalyst, it's also relevant, and it's the same, but it relates to the active site. And since active sites are quite difficult to define, we usually define it per gram or per square meter of catalyst surface area, or square meter of metal surface area in the catalyst, just for practical reasons, because it's so difficult to actually assess the number of active sites. The turnover frequency is then, of course, the turnover number divided by a unit time. And I always tell my students to make sure that they define the unit, because this is one of those things that can confuse people. So make sure that you write out your definition, if it's per gram or per square meter or whatever, and also what unit time you're using. Space velocity is another important part in talking about communicating catalysis. It's basically the inverse of space-time, and it's defined different for homogeneous and heterogeneous systems. For homogeneous, the space velocity is the flow rate coming into the reactor defined at normal temperature pressure divided by the reactor volume. And if the unit of Q is hours, we call it the volumetric hourly space velocity. And in homogeneous catalysis, we assume that the catalyst is so well distributed in the system that all of the reactor volume is active. In heterogeneous catalysis, you can't really make the same assumption, because the important part is not the reactor volume, it's the amount of solid material you have inside the reactor. So we take and we define weight hourly space velocity as the incoming flow rate divided by the weight of the catalyst, or indeed the gas hourly space velocity as the flow rate at normal temperature pressure divided by the catalyst volume. And this is always defined as normal temperature pressure, even though the reactions are operating at high temperature pressure in real life. And then we get a unit, which is inverse seconds or inverse hours or so. Or in the homogeneous case, per cubic meter of catalyst or per cubic meter of reactor volume. If you look at typical operations in chemistry, steam reforming, which is strongly limited by heat transfer and equilibrium constraints. We see rather low space velocities, so between 1 and 3,000 inverse hours. That means that 1 cubic meter of catalyst processes 1,000 to 3,000 normal cubic meters of gas per hour. For total oxidation, which is a much faster reaction, we can operate between 10 and 50,000 inverse hours. In ammonia, which is also equilibrium constrained reaction, between 5 and 10,000 inverse hours. Hydrodesulfurization is about 1, but here we have a weight hourly space velocity, which means that we have 1 cubic meter of oil processed per cubic ton of catalyst per hour. And then, depending on where we position a catalyst for removing NOx, selective catalytic reduction of NOx, we actually end up with different space velocities. So if we have a position which has quite a lot of dust, we need to have a very open catalyst structure to let this dust pass through the catalyst without clogging it. So then we use a very open catalyst structure, but then we can squeeze less catalyst mass into the equivalent volume. So we need lower or more volume to get decent conversion. If we put it in a low dust position, we can increase the channel density, or what the amount of catalyst in the system. We reach somewhere between 6 and 10,000 inverse hours, and in a tail end without dust, you can go as high as somewhere between 8 and 12,000. Then there's just some general reaction rates. This is more chemistry than catalysis, but we need this for the discussion later on. So if you have a batch reactor and we have a reaction A going to B, the derivative or the reaction rate is defined as the negative derivative of component A and the positive time derivative of component B. And we can define the reaction rate as R, which is the reaction rate. It's a constant time the concentration of a component. And then we can increase the complexity, we can add stoichiometric factors, and it only complicates the reaction, but it's still manageable. And we can then express this as this expression, or actually with the reaction rate, we can expand the reaction rate constant, and we can use the Arrhenius equation to do so. So the constant is a pre-exponential factor times the natural logarithm of the activation energy divided by the gas constant and the temperature. So the activation energy is a key parameter in catalysis, and you can generally say that for chemically controlled systems, we'll come back to later what that means, this constant doubles for every 10-degree increase as a rule of thumb, which shows you that these reactions are strongly temperature dependent. And if you have measured your activation energy, it'll most likely be somewhere between 8 and 100 kilojoules per mole. And if it's below 20 kilojoules per mole, it's not likely to be limited by chemical reaction. It's rather limited by other things like transport of reactants to the catalyst surface. Then the pre-exponential factor is a representation of the number of collisions between the molecules, and it's usually somewhere between 10 to the power of 11 and 10 to the power of 14. And by performing activity measurements or measurements of conversion, reaction rate, at different temperatures, we can plot the logarithm of the calculated K value as a function of the, or the other way around, the inverse temperature as a function of the reaction rate, and the slope here will actually produce our activation energy. But as I said, if we increase temperature, we will actually run into other reaction regimes where other things limit the reaction rate. So if we start at low temperature and increase, we have a regime here where we have a reaction which is controlled on the reaction surface, and then it's the normal reaction. So it's the heterogeneous reaction divided by the gas constant. But when we start increasing temperature, we actually consume the reactants faster than we can get them to the surface. And then we get into a diffusion limited system where the transport of reactants inside the catalyst, this is for heterogeneous catalysts, inside the catalyst is the rate limiting step. And at a certain point, if we continue to increase the temperature, we will actually have difficulty to, or the limiting step is transferring material from the bulk of the gas to the catalyst surface. As soon as it gets into the catalyst, it will be converted into whatever we want. And for this pore diffusion limited, the slope is about half of what it is for, in this case, the intrinsic controlled surface. And for the mass transfer controlled, it's actually rather constant. So it's the homogeneous divided by, so it's this one. It's actually a constant where it's somewhere between 4 to 12 divided by the gas constant. So it's actually a fixed number, and it's not dependent on the reaction. And if you increase the temperature, of course, you will get into a regime where your catalyst is melted and your homogeneous reaction dominates again, which is then the same as you have down here. We have catalytic cycles. I told you that we have this change to the site, and we have something going on, and then we come back to the original site. And these catalyst cycles, there are several, actually can be many small reactions or steps. However, fortunately, one of these is always the slowest one. And the entire cycle is determined by the rate of reaction for this single step, this single rate limiting step. So it's more like an hourglass, one constraint that controls the flow, and it's not a sum or an average of all of these reactions. So if you express it differently, you have all these different reaction and activation energies, but it's only the highest one that determines the actual reaction rate. Reaction order with all of these steps involved can be quite complex, but since we have this rate limiting step, we can almost always reduce it to a 0, first or second order reaction. So we have 0 order reaction, first order reaction, second order reaction expressions, and we can use those to estimate almost all of the catalytic reactions out there. But when we add catalyst, we do of course change the reaction rate. So we have to introduce some change to the rate law. So we add the concentration of the catalyst, we add an exponential factor, and then we can express the kinetics of the catalytic reaction in different ways. And these different ways of thinking of the catalyst reaction have different names, or actually named after the guys inventing them. Langmuir Hinsselwood, Eli Riddell, and Michaelis Menten are a few different. And There are, of course, more, but let's stick with these standard ones. So in Langmuir-Hinshelwood, we have an adsorption of gases on a surface. So both or if we have two reactants, both of them land on the catalyst surface, they adsorb on an active site, and the reaction happens on this active site and the products desorb. Then you can, of course, include also the diffusion to and from the active site. Reactions that are well described with the Langmuir-Hinshelwood kinetics is steam reforming on nickel catalysts, ammonia synthesis on iron catalysts, for instance. Eli Riddell differs slightly in that it's only one of the reactants. So if you have two materials or two molecules that should react, it's only one of the materials that adsorb on the surface of the catalyst. Then the other reactant comes directly from the gas phase and reacts with the pre-adsorbed molecule. And then the products desorb. So NOx removal is a really good example where you have an acidic catalyst which is completely filled with ammonia, and the NOx molecules lands directly on the ammonia and reacts into nitrogen and water to be removed. These two, Langmuir-Hinshelwood and Eli Riddell kinetics, are relevant for heterogeneous catalysis, while Michaelis-Menten is used to describe enzymatic reactions and homogeneous catalysts. And it's basically a reaction between the catalyst and a reactant, and it forms a reversible complex. So something that can go back and forth between the original state and the reactants, but also decompose into the product. Enzymatic reactions, homogeneous catalysts are well described with this. So to be able to do any type of catalysis, there has to be interaction between the catalyst and the material. But this interaction cannot be too strong and it cannot be too weak. So the adsorption, the reaction, the complexation can't be too strong. So if it's too strong, the reactant or the product can't leave the catalyst, and we call this poisoning. And this interaction principle, that it's not too strong and not too weak, is usually referred to as Sabatier's principle or the Goldilocks principle of catalysis. And we use the heat of adsorption as the functional parameter, and we do these kind of volcano plots to see where we are. So if you have a very low heat of adsorption, you will have very little adsorption of reactants on the surface. As the heat of adsorption increases, the reaction rate will go up, but at a certain point, you will actually start to see a decrease in reaction rate again because the products can't leave the active sites. And then you can try different materials, different metals, and you can plot them into these volcano plots to show the actual concept. So to summarize, we have a very important concept, which is the active site. And the active site is never empty. So there's either a reactant or a product or some kind of intermediate or indeed a spectator atom. So it's never empty. The active site is always recovered. So it's reformed after reaction. So it's not consumed in the catalytic cycle, or if it's consumed, it's to a much lower degree than stoichiometry. We can't change nature, so catalyst does not change the ultimate equilibrium. We differentiate between heterogeneous and homogeneous catalysis, and I will talk much more about that now, starting with homogeneous catalysis and then turning to heterogeneous catalysis. And then you can describe the reaction mechanisms, the kinetics, with different adsorption models like Langmuir-Hinshelwood, Eli Riddell, and Michaelis-Menten. Homogeneous catalysis cover all type of reactions where the catalyst and the products are in the same state of aggregation. The most common ones are liquid-liquid, but there are a few examples of gas-gas catalyzed reactions. I know only of the lead chamber process, the original process for synthesizing sulfuric acid, but I'm sure there are a few more. In homogeneous catalysis, there is normally just one very well-tailored active site which has a well-defined chemical composition. And this is very unlike the case for, or the normal case for heterogeneous catalysis. It's homogeneous phase catalysis also when the reaction involves gases, but to react, these gases has to be dissolved in the liquid, and since they're in the liquid, we still call it homogeneous phase catalysis. To a large extent, this area has become synonymous to organometallic complexes, but there are also acid and base materials that are homogeneous catalysis. Major issues are catalyst activity, reaching high enough activities, catalyst life. The catalyst has to be able to perform a large number of catalyst cycles before deactivating. And finally, catalyst separation and recovery. Since we have them in the same phase, getting the catalyst out and recycled back is a really important part of an economically feasible production. Catalysts, they can be acids, they can be basic, they can be organic compounds, or they can be this organometallic complexes. Here are a few examples. The two organometallic complexes with rhodium in the center and different ligands. And here we see a hydrogenation reaction, so adding hydrogen to an unsaturated bond. And this is the oxo reaction, where you add CO and hydrogen, forming the aldehyde. To make a catalytic cycle in homogeneous catalysis, we talk about elementary steps. These elementary steps are normally found in organic and complex chemistry. They can be dissociation and coordination, oxidative addition, reductive elimination, the insertion and migration reactions, deinsertion, beta elimination reactions, which are the reverse of the previous ones. And it can also be nucleophilic attacks on coordinate substrate. And since it's a limited number of cycles, we can actually, in a quite intricate way, construct new cycles in theory and then try them out experimentally. Here you can see the different elementary steps. So we talk about ligand coordination when we add a ligand. Ligand can be removed again, so ligand dissociation. We can have a migratory insertion where we insert a group in between, this CO is moved here, and it can also be moved to the same metal in this case. Then you can go backwards in this direction. You can do nucleophilic attacks. You can do reductive elimination as well, as well as oxidative addition with different materials. And we can then take this and we can build up these catalytic cycles. So here is the oxo reaction, a hydroformylation of propene. So we start with a rhodium complex. We have ligands, and we have CO. CO coordinates to the rhodium. We add the propylene. We lose one CO in the process. We end up with propylene here. Add another CO, which forces the rhodium to transfer into the, using this double bond here. Form another CO adding here, going in between the rhodium and the former propylene. And finally, we use hydrogen to saturate this bond to release it, and we reform this catalytic complex again. So one full cycle, we consume one CO and we consume one hydrogen to form the butyric aldehyde from propylene, CO, and hydrogen. So to summarize, homogeneous catalysis is when the catalyst and the reactants and products are in the same state of aggregation. It is a very well-defined active site chemically. We have elementary reactions that build up a catalytic cycle. We work with predominantly organometallic catalysts, but also acids, bases, and other materials can be active. Production of acetic acid, production of these aldehydes by the oxo process are nice commercial examples, but also very much in fine chemical production is based on these type of catalysts. And the production of these homogeneous catalysts are also as fine chemicals. The most important part to economic operation, aside from activity and selectivity, is of course the recycle and recovery of the material. We can't lose too much rhodium, for instance, with the products. All right, with that said, we'll now turn to heterogeneous catalysis. Heterogeneous catalysis is really, as I showed initially, a workhorse of the chemical industry. 90% of all chemicals that you see around yourself, or all the material that you see around yourself, is in fact some kind of chemical, and 90% of that has been in touch with a catalyst in the production. Heterogeneous catalyst in itself is also a specialty chemical market. So we have about 800,000 tons of catalysts produced annually. It's a large market, so somewhere between, well, almost 30 billion US dollars in market cap, and it's growing. The growth is mainly triggered by more stringent environmental legislation and a desire to do more with respect to the materials that we process. The standard case is that we have a gaseous reactant over a catalyst at a rather high temperature. I know that high temperature is very relevant, but high temperature can be up towards 800 degrees, but normal case may be 200 to 400 degrees C. The nice thing with heterogeneous catalysis is that it combines so many different areas of research. You have material science, we have surface chemistry, we have surface science, we have thermodynamics and kinetics, we have solid state physics, inorganic and organic chemistry, but also engineering aspects that are important to understand the phenomenon of catalysis and transform it into something that is useful to industry. It's also an area with a lot of research activity. There are so many books on the subject. There are many research papers. This is a rather old figure. I'm sure it's well north of 18,000 papers now. But unfortunately, fortunately for all of us, we don't have to read all of these materials because the subject relies on a few fundamental principles, and I will try to touch upon these now, and then we go into more in-depth with the future webinars that are upcoming. The structure is an important part. So in industrial catalysts, we have three parts. We have the carrier, we have the support, and we have the active phase. Three very important aspects of heterogeneous catalysis. They all have their own purpose. So for instance, the carrier is there to provide the structure to the reactor bed. It determines heat and mass transfer. It also gives us the bed pressure drop, so how much pressure is lost over moving the gases through the reactor. The carrier can be either ceramic or metallic, and one important aspect to the carrier is that it has to be resistant to mechanical stress. These are typical catalyst carriers. So we have like extrudated materials that are porous. We have ring-shaped materials that can be either extrudated or tableted. In this case, it's extrudated. We have also monolith type structures, which you find in your catalytic car converters, for instance, but also in many other industrial applications. The support, which is the second part of the catalyst, is what provides the surface area for the reaction. So in order to have any type of reaction, we need somewhere where the reactants can meet and form products. The larger the surface area, the more space for those kind of meetings. And the support can actually be the same material as the carrier, so we can make extrudates out of aluminium oxide, alumina, and use that as a support. And aluminium oxide is a very common material for the support, but so is also silica, silicon oxide, ceria, other mixed oxides, as well as activated carbon. And as I said, the surface area is really important, so we measure that. The square meters per gram is the measurement that we normally refer to. And to achieve a high surface area, we need high porosity. So we differentiate in porosity into micropores, which are smaller than 2 nanometers, mesopores that are between 2 and 50 nanometers, and macropores that are larger than 50 nanometers. And if we pinpoint some of these materials, you can see that the actual surface area range somewhere from 200 to more than 1,000 square meters per gram. And to give you some idea of how large surface area that is, a football field is about 7,000 square meters, which is about the same as 40 grams of gamma alumina. So the inside of these materials have very, very large surface areas. Finally, we need an active phase. This is where the sites are and where we do form the reaction, or the reaction occurs. It can be metals, it can be metal oxides, it can be acid or basic groups on solid materials. Most common, we have metals from the transition metal group in the periodic table. So like here in the middle, iron, cobalt, nickel, copper, ruthenium, rhodium, palladium, platinum are all common catalyst materials. And they have this property where they interact enough with the reactants and products, but not too much to be inhibited. That, on the other hand, that feature we find to the right-hand side in the periodic table, where we have strongly electronegative atoms or heteroatoms that interact very strongly with the surface. So sulfur, phosphorus, arsenic are very well-known catalyst poisons. But as I said, it's not enough to just do a nice catalyst surface area. We actually span a huge band in distance in catalysis. So we start with molecules. Here we have some kind of reactant. It adsorbs. These molecules are usually point something angstrom. We have an active site on a catalyst where we form our products. They desorb. Then we take this surface, which is usually prepared in a powder form, and we can compress them into tablets or pellets or something that gives us a structure to the bed, so form a carrier. We take this carrier and we pack them into a reactor, and we process reactants and products. So we start somewhere, point something angstrom. We have these clusters of metal, for instance, that are on the order of 1 to 5 nanometers. We have them supported on powders that are maybe micrometer sized in diameter of the powders. Then we form millimeter large carrier tablets, And then we have reactors that are maybe 1 to 10 meter in diameter. So we work somewhere on maybe 12 orders of magnitude in catalysis, which is to me a nice summary of the uniqueness of this area. Coming back to the active site, these surfaces that we produce are not as perfect as we believe. There are kinks, there are steps, there are other crystal imperfections like vacancies that often prove to be the active site. So if you look at these nice crystals, you see that sometimes there is a surface cluster where there are some extra atoms on top. You have kinks in the edge, you have Terence vacancies or step vacancies like this, or indeed a step. And they are most often the active sites, and they're actually most often not the preferred adsorption site, because the preferred adsorption sites are usually inhibited because they're too strong, so too strongly adsorbed too. So we follow the Sabatier principle. It's good enough for adsorption, but it still allows for desorption of the products, and these imperfections can actually help in forming these properties. And ideally, all sites should be alike and not in contact with each other, but that's definitely not the case in industrial catalysis. And then I, in this discussion, separated the support from the active phase, but that's not always true, because we have a case where we have a strong interaction between the metal and the support. So if you have a metal active phase and you put it on a support, there can actually be spillover effects where the support interacts with the metal in the catalytic cycle. Three-way catalysis is a good example where oxygen from the ceria is actually involved in the oxygen transfer to, for instance, CO forming CO2 on the rhodia, or on the on the rhodium. In addition to these three main components, we can add promoters and modifiers, which we add to the active phase, to the support, or to the carrier. And the purpose of adding these, and the addition can be as low as 0.1 to 1 mole percent of the active phase, for instance. And we do that to promote activity. We can also decrease activity in some cases if we want to avoid hotspots. It's to block side reactions, so improve selectivity. It can be to prolong catalyst life. It can be, if we add it to the carrier, to improve textural properties, adding glass fiber, for instance, to make the inorganic material more tolerant to mechanical stress. These are normally based on empirical observation, and they're long-term effects, so they're often left out of academic research. We talk about catalysis. In my world, you talk a lot about catalysis, but I understand if other people have it differently. But when we talk about catalysis, we use a certain syntax. And since it's oftentimes uncertain what phase is active when we actually put it inside the reactor and we operate it. So it can be the metal that is active, but it can also be an oxide or a sulfide of the metal, but it can also be a very strange combination where you have an oxide but it's metallic on the surface because the surface is reduced or something like that. So we never go into too much detail about the phase of the material. So we just keep it simple and we talk about COMO, for instance, cobalt molybdenum on alumina. So in this case, it would be cobalt and molybdenum, that is the active phase, and then we use a dash or slash to separate it from the support. And in this case, it would be aluminum oxide. An important part of understanding heterogeneous catalysts is the characterization. And characterization is what we call the understanding of the catalyst material in more detail. We use something called fine particle analysis, where we look at the surface areas, physisorption, chemisorption, etc. We also use temperature program methods. We also do a lot of spectroscopy, microscopy methods, looking at the crystal structures and the shapes and forms of these materials. And as I said, surface area is a key method. So understanding the reactants of this to the surface is, so how accessible is the surface to the reactants? That is something that you understand with these methods. And we use adsorption with different probe molecules, or indeed we rely on physical phenomena. So we do physisorption with nitrogen, which is called the BET method. We can also use mercury intrusion porisometry to understand the macro and mesoporosity of the material. And we do use chemisorption, where we're sending different probe molecules. It can be ammonia for acid sites or CO2 for basic sites, just to understand more of the surface that we're working with. We differentiate physisorption from chemisorption. And then we can do this either under steady state conditions. We can also do it under temperature programmed situations where you're increasing the temperature. So for instance, you can look at the changes that happens to a catalyst when it influences the environment. So it can be a temperature programmed reduction, temperature programmed oxidation, desorption, or indeed looking at a reaction. And it gives you a fingerprint, and it's a suitable thing to compare in between a series of catalysts, but you can also use it for at least understanding what materials are, for instance, reducing at certain temperatures by looking into literature. You can also use it to calculate heats of adsorption and things like that. Spectroscopic methods use bulk or surface sensitive methods using different types of radiation. So it can be X-rays, it can be Raman spectroscopy, electron microscopy, X-ray photoelectron spectroscopy, and we talk about ex situ or in situ studies, where ex situ is the powder outside of the reactor, in situ is where you have the catalyst inside the reactor, or at least trying to mimic the conditions inside the reactor. Testing is important for many different reasons. So once you understand the nature of the catalyst that you prepared through characterization, the next step would be to see how it performs with respect to your desired reaction. But catalyst testing is, as I said, important for several reasons. It's, first of all, for finding new catalysts. So looking at new material, how active, selective are they? What are their kinetics? How do the reaction mechanism look at these surfaces? But it's also for doing catalyst diagnostics. So if you have an industrial reactor, you can extract a small sample from that, and you can run a diagnostics test in a smaller microreactor to see how the catalyst mass is faring, how much life can you expect to be left in that reactor. And catalyst lifetime is also something that you want to investigate. And we select the reactor we use for small-scale testing differently, depending on what we want to achieve. So if we're looking at just finding new catalysts, we are using a scouting reactor. For improvement industrialization, we can use a catalyst optimization reactor. And for pilot testing, we use prototype reactors. In scouting reactors, it's important that it's easy to measure activity. We want minimum influence of gradients. Gradients are normally temperature and pressure, so temperature and concentration, so diffusion come into play. And we want it to be easy to exchange the catalyst, because here we're talking about investigating many different catalysts in short periods of time. And we try to measure parameters that are not influenced by heat and mass transfer. We try to measure the intrinsic kinetics, but if that's not possible, we estimate the influence of heat and mass transfer using numerical methods. And in the catalyst testing webinar, we will be talking much more about this. These gradients are interparticular, interparticular, or reactor specific. So they're either inside the actual catalyst pellet, they're in between the catalyst particles, or they can be in the reactor level. These criteria were first introduced by Mears in the 70s, and then there's been quite a few publications about this since. And it's all about finding the reaction rate without influence of outer or inner mass or heat transfer. And does that matter? Yes. If you have exothermic reactions, you can actually overestimate the actual reaction rate with almost a factor of 100. So that gives you a very bad experience when you're going to scale up, having overestimated your activity with 100 times. And as we pointed out earlier, you can actually also use the activation energy to assess the gradients. In the catalyst optimization reactor, we bring successful candidates towards commercialization. We prepare and we test catalysts in a satisfactory commercial form, like pellets, extrudates, or monoliths. And we investigate the performance closer to industrial conditions. And here we actually do want the gradients to understand what happens in the reactor after scaling up into a larger reactor. And the next scale-up step would be a prototype reactor, where we have a large enough section of a commercial type reactor to be representative, and we use it to determine reactor gradients and performance like pressure drop, but also how well can we repeat the reactor packing, what are the heat transfer limitations, and a good example is a single tube in a multi-tube reactor. Test reactors can be of different types. They can be non-stationary, like batch or fed batch, transient reactors, semi-batch reactors. They can also be stationary, like continuous reactors, like plug flow, fluidized bed, or CSTR reactors. And you can break it down like this, that you have your laboratory reactors, you have your non-stationary reactors, where you have batch, semi-batch, or fed batch, transient reactors. On the stationary side, we have our continuously stirred tank reactors, we have fluidized beds, and we have plug flow reactors. Plug flow reactors can be integral or differential of nature, meaning that you have high or low conversion. The differential reactors can be either single pass or recirculating, and the recirculation can be either internal or external. But we'll go more into details about this at a later time. Catalyst manufacturing. This is sort of a black box. This is something that you find very little about in literature, about how it's actually being done in industry. But we'll try to go through a little of the steps here, and then there's a separate webinar on just manufacturing. But there are steps involving the preparation of the support, adding the active phase. There's also post-treatment, forming, and activation of the catalyst. And we talk about two main classes of catalyst. It's either bulk catalyst, like ammonia synthesis, hydrocracking, zeolites, where the entire material is consisting of the catalyst material. Then you have the impregnated catalyst, where you are more careful with what you do with the actual active phase. We can break it down again. So we have bulk catalyst to the left, can be formed by precipitation, hydrothermal synthesis, or some kind of fusion alloy leaching. And then we have the impregnated catalyst, where we start with pre-shaped bodies of, for instance, aluminum oxide. We add the actual noble metal, for instance, via either wet impregnation or incipient wetness impregnation. And then you have also ion exchange for acidic zeolites, for instance. Support preparation consists of gelation and precipitation operations. You do active phase preparation through impregnation and ion exchange. Post-treatment includes filtration, drying, and calcination. Forming operation can be extrusion and pelleting. And then you have activation that can be reduction or sulfidation, for instance. All right, final thing is deactivation. So we have, as stated before, a slow change to the catalyst activity, which we normally refer to something related to deactivation. And this deactivation can have several causes. So it's over temperature, so overheating the catalyst. It can be that you change the inlet composition to include new things or higher concentrations of something. Another important thing is process hygiene. So how well is the upstream cleaning operations being done? And this is concerning the deactivation that occurred after the first initial lowering of activity. When you have a fresh catalyst, you have a certain activity, but it sort of settles in and drops down to an unstable activity after maybe 50 to 100 hours. So deactivation to me is something that happens after these 50 to 100 hours. And it can be either a chemical poisoning, where you have a metal, you have oxygen, sulfur, CO landing and absorbing too strongly. It can be fouling, where you cover the physically block the pores, either with solid carbon, as in this case, or something that is entering with the gas stream, like ash. It's also sintering of the active phase, where small clusters form larger clusters, or it's sintering of the support, where it closes up and you have active phase that is not accessible to the material anymore. Poisoning is a very strong interaction with the active phase. It's usually an electronegative species like sulfur, chlorine, arsenic, or phosphorus, but it can also be other compounds like CO, oxygen, or ammonia. And as already pointed out, we find it here to the right in the periodic table. Fouling is when we cover an active part of the catalyst. It can be physical blocking of active sites, but it can also be physical blocking of pores, making parts of the catalyst useless. And coke can be formed inside, so the fouling agent can be formed inside. It's very difficult to avoid that if you have a reaction forming solid carbon. It can also be that it comes from the outside. It's introduced, like ash covering the material in biomass combustion and denox, for instance. Sintering, two types. We have the active phase sintering, which is normally resulting in high temperature. And then you have the support, where the support sort of forms these larger or smaller pores, or actually closes up the pores. And it's both the same in that you lose metal surface area, either directly or indirectly. So finally, to conclude, the catalysis is omnipresent in industry. It accelerates the reaction and favor chosen products, but it can't change nature. And we differentiate between heterogeneous and homogeneous catalysis. And with that, I would like to thank you very much for listening. I will, of course, answer any questions you have if you send them to me, or if you've uploaded it through the chat function. We will be answering those afterwards. Please feel free to download the handouts. These handouts will also be sent to you via email after the webinar, and the webinar will be available for re-listening at the online service. So thank you very much for listening.